Hi there, everyone, and welcome to week 3 of our exam countdown with TheMathsTutor.ie. Today we're going to have a look at complex numbers and in particular De Moivre's theorem. So the full members, you will have access to a range of resources on your exam countdown page. But for any of you that are not full members, if you're new here, I have posted some links to videos in the chat. So you will see the first one there is the proof of De Moivre's theorem, the proof by induction. And the second one is just an example of applying De Moivre's theorem in a question from the 2018 exam paper. So those are for you to look at maybe after this live lesson or at some stage over the next week or so. So we'll get straight in. You will be familiar with from last week, we looked at changing numbers to polar form. So you'll be familiar with the complex number in this form, r cos theta plus I sine theta. So you'll remember from last week, we said r was our modulus, or the distance of the complex number back to the origin, and theta was our argument, or the angle that the complex number makes with the positive sense of the real axis. So up here, up at the top, you will see that I have shown just from your log tables, this is our De Moivre's theorem. That's our statement for De Moivre's theorem. Really, we are interested in that part of the theorem. We don't use the last part so much. De Moivre's theorem is hugely important in paper 1. It's something that comes up in the complex numbers question almost every single year. So you will find that theorem on page 20 of your log tables if you're looking for it. So where do we use De Moivre's theorem? Well, you'll see from the formula up here, we use it if we're raising a complex number to a power. So we use it in two ways. The first way, if we're raising a complex number to a power, so raising a complex number to a power. And the second way we use De Moivre's theorem is for finding roots of complex numbers. So we're going to look at both ways today by using a couple of exam paper questions as examples. So finding roots of complex numbers. Okay, so what do I mean by raising a complex number to a power? Well, for example, if I had a complex number, for example, 1 plus 3i maybe, and I was asked to raise that to the power of 4. We used De Moivre's theorem to do that. But first, as you'll see from page 20 of your log tables, the complex number first needs to be written in polar form. What do I mean by finding roots of complex numbers? Well, for example, if I was asked to raise that complex number to the power of 1/4, that's exactly the same thing as being asked to raise the complex or to find the fourth root of the complex number. So you'll see over here on the right hand side of the page, just to remind yourself of your laws of indices, the square root of x is exactly the same thing as x to the power of a half. That means the cube root is the same thing as x to the power of a third, and the fourth root is x to the power of a quarter, and so on. The fifth root would be x to the power of 1/5. So that's what I mean by finding roots of complex numbers. If we were asked to find the fourth root of 1 plus 3i, that would be exactly the same thing as asking us to raise 1 plus 3i to the power of 1/4. Just a different way of writing it. So how do we do it? Well, if we're asked to raise a complex number to a power, the first thing we do is we write our complex number in polar form. And nice and simple, the second thing we do is we apply De Moivre's theorem. Okay, so we're going to have a look at that in a second. If I'm asked to find roots of complex numbers, the first thing I do again is I write my complex number in polar form. The second thing I do is I write my complex number in general polar form. And what general polar form means, that all that means is to my argument, I add n times 360 if my angle is in degrees, or n times 2 pi if my angle is in radians. So 360 in degrees or 2 pi in radians, that's just one full rotation of the circle. So we're basically saying, when we're writing it in general polar form, that we can go around that unit circle as many times as we want, n times in fact, where n is just a positive integer. The third thing we do is we apply De Moivre's theorem, just as we did over here when we were raising a complex number to a power. And the last thing we do is we let n equals 0, 1, 2, 3 as the question requests. So we will know by looking at the question how many answers that we're looking for. So just to go through that again, if your power is a whole number, like 3, 4, 5, we just change our complex number to polar form and apply the theorem. If your complex number is raised to the power of a fraction, so if it's a fractional power up here, we need to add in this extra step of general polar form, and then because we'll have an n in our answer, let n equal 0, 1, 2, 3 as requested in the question. So let's get straight in. The first thing we're going to do is raising a complex number just to a regular whole number power. So this question is from the 2017 exam paper 1, and we're looking at question 2, part A. So we're given our complex number up here. It's in Cartesian or rectangular form, so a plus bi, and we're asked to use the Myers theorem to write z to the power of 4 in Cartesian or rectangular form. So we need to remember, when we get our answer, we need to give it in this form, in rectangular or Cartesian form. This is nice and straightforward. We're given z and we're asked to raise z to the power of 4. So this is where our complex number is raised to a power, but my power is a whole number. So first step is to write our complex number in polar form. So to remind ourselves from last week, minus root 3 plus I, the first thing I'm going to do is I'm going to draw my complex number. Just a rough sketch, just my real and my imaginary axis. My minus root 3 is out to the left of my real axis, plus I is going to be up here in this quadrant. So I'm going to join that back to the origin, draw in my modulus, and I'm just going to create my little triangle here down to the real axis. I'm going to mark in my distances. So this distance here is a distance of root 3, not minus root 3. It's minus because it's to the left, but the distance itself is just root 3. This distance up here is 1, because in order to get to that complex number there, I went out minus root 3 and I went up 1. Okay, so the first thing we do, remember we want to write this in polar form. So r cos theta plus I sine theta. The first thing we're going to try find is our modulus. So remember, that's going to be the square root of the real part squared plus the imaginary part squared. And when you do that, when we throw that into our calculators, we should be getting a modulus of 2. So that's what I'm going to put in here for r. Next, for my theta, so theta, remember, is my argument. And remember from the last day, it always comes from the positive sense of the real axis. So that there, anti-clockwise from the positive real axis, that's my theta. Before I can find theta, I'm going to need to find my angle in here, which I'm going to call it angle A for now. So I have the opposite, I have the adjacent. Let's make that triangle just a little bit bigger so you can see it. That's 1, that's root 3, and there's my angle A. I have my opposite, so my opposite is 1. My adjacent is root 3, so we know that we're going to be using tan. So the tan of my angle A is opposite over adjacent 1 over root 3. Again, there's no need for me to put in that minus root 3 because it's just the distance I'm looking for. So tan A is 1 over root 3. And from that, we can find A by finding the tan inverse of 1 over root 3. So throwing that into your calculator, my calculator is in degrees, so I leave it in degrees. That should give you an angle of 30 degrees. The question doesn't specify whether the angle needs to be in degrees or radians, so it's completely up to you. Okay, so remember, this little angle in here is 30 degrees, but we're interested in theta, which was this angle coming around to here. How will I find what theta is? Well, the full semicircle would be 180 degrees, so my theta is going to be 180 minus my angle A, 180 minus my 30. So that's getting 150 degrees for theta. So in polar form, my Z is going to be, let's just change the color here. So my Z is going to be R, which was 2 from up here, times cos of theta, which was 150, plus I times sine of theta, which was 150. And that's the first part of my question done. That's writing my complex number in polar form. But remember, they asked us to find z to the power of 4. So our job is to raise this complex number to the power of 4. In other words, raise this complex number to the power of 4. So let's remind ourselves what De Moivre's theorem told us. De Moivre's theorem told us that if we have a complex number and we're raising it to a power, we raise the modulus to the power and we multiply the angle by the power. So back to this one, we're going to raise the modulus to the power, so 2 to the power of 4, and we're going to multiply the angle by the power. So that would be 4 times 150 plus I times the sine of 4 times 150. So what have I done there? Let me highlight it. I've raised my modulus to the power of 4 and I've multiplied my angle by 4 because that's me applying De Moivre's theorem. That's what De Moivre's theorem told me to do. So that's going to give me 2 to the power of 4 is 16. Cos of 4 times 150 is 600 plus I times the sine of 600. Okay, that's my number written in polar form. That's my De Moivre's theorem applied to my complex number. But remember, they asked us for our answer in rectangular form. So all that's left to do is to throw this into our calculator. So for the real part, it's going to be 16 times cos of 600. That goes into my calculator and I should be getting minus 8. For the imaginary part, it's going to be the 16 times the sine of 600, and that should give us minus 8 root 3, I, because it's the imaginary part. So in short, just to recap, we've first of all written our complex number in polar form right here, and here we've applied De Moivre's theorem. We've checked our answer, and our answer should be in rectangular form, so that's exactly what we've done there. Okay, and that's an example of applying De Moivre's theorem when your power is a whole number. Okay, so remember we said back up here, we've 2 uses for De Moivre's theorem. Number 1 is raising a complex number to a power. That's what we've just done. Number 2 is finding the roots of complex numbers, and that comes into play when our power is a fraction. Okay, because the fourth root is the power of 1/4. So next question we're going to have a look at is 2019, and this is again from paper 1, and it's question part B. Okay, so to start with, we're given a complex number. V is 2 minus 2 root 3i. The first thing we're asked to do in part 1 is to write our complex number in this form. In other words, change it to polar form. But be careful in this question. Look what they're telling us about the angle. The angle needs to be somewhere between 0 and 2 pi. In other words, our calculator must be in radians. That's our hint to put our calculator in radians. So first thing I'm going to do, as I always do, I'm going to draw a rough sketch of my complex number so that I know where it is on the argand diagram. So we're going across 2 on the real axis and we're going down minus 2 root 3 on the imaginary axis. So my complex number is in that quadrant. I'm going to join it back up to the origin for the modulus, and I'm going to create my triangle from the real axis. I know that the distance across here is 2, and I know that the distance on the imaginary axis, just the distance, remember, is 2 root 3. It's minus because we're going down, but the distance is 2 root 3. Okay, it's a right angle triangle because I've made it that way, and my first job is to find R, which is my modulus. So that's going to be the square root of my A, which is 2 squared, plus my B, which is minus 2 root 3, the imaginary part. So be careful putting that into the calculator. Make sure everything is in brackets, and your modulus should work out to be, again, 4. Okay, the second thing, so that's my modulus. The second thing for polar form is my theta. So remember, as we said the last time, your theta always comes from the positive sense of the real axis, and it always goes anti-clockwise like this. So that in blue is going to be my theta. This triangle here, I'm just going to make it a little bit bigger for you. That triangle there is going to help me to find the angle. I'm going to call it A. So again, we're always using tan because we have opposite and adjacent. So we're looking at the tan of angle A is the opposite, which is 2 root 3, over the adjacent, which is here, 2. So the tan of the angle A is opposite over adjacent, 2 root 3 over 2. From that, we can find A by getting the tan inverse of 2 root 3 over 2. So that should give you a value for A. Remember, your calculator must be in radians. Your value for A should be pi over 3 in radians. Okay? So A is not what we needed for polar form. Theta is what we needed for polar form. So remember, this here is my theta, that whole angle all the way around there. The full circle would be 360 degrees or 2 pi. So my theta is going to be 2 pi minus my angle A. I just want what's highlighted in blue here. It's not all quite the full circle of 2 pi. It's this little tiny bit short. It's that pi over 3 degrees or pi over 3 radians short. So 2 pi minus pi over 3 should give you 5 pi over 3 for your theta. So in polar form, my complex number, which was V, that's it in Cartesian form. In polar form, which we're asked for, is R, which was 4, times the cos of 5 pi over 3, which was theta, plus I times the sine of 5 pi over 3, which was my theta. And that's my answer. That's what they've asked me to do. They've asked me to write it in polar form. Okay, so moving on to part 2 of that question, use your answer to part B, part 1. So let's just write that down straight away. My V was 4 times the cos of 5 pi over 3 plus I times the sine of 5 pi over 3. So I'm just carrying that forward from part A, part 1. And they're asking me to find the 2 possible values of W where W squared is equal to V. Okay, so loads going on here. And this is where lots of people get confused in complex numbers, De Moivre's theorem questions. There's 2 hints in the question that tell us that this is a question where we're going to have a fractional power, or this is a question where we're looking for the roots. So find the 2 possible values. They've highlighted for you in the question. They've put it in bold. That must be really important. We're expecting more than one answer. We're expecting 2 answers. And the second hint is our equation over here. So we're looking for W, and they're telling me that W squared is equal to V. And again, bear in mind, they're looking for your answers in Cartesian or in rectangular form. So we'll worry about that at the very end. So the equation they're giving me is W squared is equal to V. And it's W that we're looking for, the 2 possible values of W. So if I wanted to get W out of this equation here, I need to get rid of the squared. So I would need to find the square root of both sides. So I'm getting the square root of the left, and whatever you do to the left, you must do to the right. But look what happens on the left when we do that. The square root and the squared are exact opposites of each other. So that just leaves me with W. On the right, I have the square root of V. But you might remember at the very start of this lesson, we said the square root is the exact same thing as the power of a half. So essentially, to solve to find W, we're going to have to raise this complex number V to the power of a half. But have a look at my power. My power is a fraction. So if I just scroll back up here, remember when we're looking at the power as a fraction, this is what we need to do. We need to write it in polar form. Then we need to add in this extra step of general polar form because we can go around that unit circle as many times as we want. Then we apply the theorem, and then we're going to have an n in our answer. So we need to let n equal 0, 1, and 2 as required. So let's go back to our equation. W is what we're looking for. V, remember, is what you have up here, what you found in part 1. So that's going to be 4 times the cos of 5 pi over 3 plus I times the sine of 5 pi over 3. And we're being asked to raise that to the power of a half from up here. So we're asked to raise v to the power of a half because w is what they're looking for. Okay, so because it's a fractional power, the first thing I'm going to do, I've already gotten my complex number in polar form, so I'm going to change it to general polar form. So my 4 stays as it is, my modulus stays as it is, but my angle, instead of being 5 pi over 3, I now need to add on n times 2 pi. Why n times 2 pi? Well, let's have a think about it. There's my real axis, there's my imaginary axis. N times 2 pi, so 1 times 2 pi would be me going around the unit circle once more. 2 times 2 pi would be me going around the circle twice more. And so on. 3 times would be 3 times around the unit circle. N times is saying that I can go around that circle as many times as I want as required in the question. Okay? Plus I times the sine. My theta stays the same, 5 pi over 3, but I add on n times 2 pi. I add on as many 2 pi's, as many full rounds of the circle, full rotations of the circle as possible. Okay? That's step 2 done. So I've written it in polar form. That came from part 1. I've written it in general polar form. And now I'm going to apply the theorem. Okay, so I'm going to raise all of this to the power of a half. So let's just remind ourselves, de Moivre's theorem tells us if we're applying de Moivre's theorem, if we're raising a complex number to a power, we raise the modulus to the power, and we multiply the angle by the power. Okay, so let's do that here. We're going to raise our modulus to the power of a half. So that's going to be 4. And I'm just going to do my application of de Moivre's theorem in red to make it stand out. I'm raising that to the power of a half. And I'm multiplying this whole angle, 5 pi over 3 plus n times 2 pi. I'm also multiplying that by a half. So I'm going to do the same with the imaginary part, plus I times the sine of 5 pi over 3 plus n times 2 pi. And that whole thing needs to be raised to the power of a half. So what I've done in red there is my application of de Moivre's theorem. I'm applying the theorem. 4 to the power of a half, well, that's just the same thing as square root of 4. So that's going to give me 2. Be careful with what happens here. We get cos of. So we're multiplying this whole thing by a half. That's why I changed it to general polar form first. When we multiply that by a half, we will get 5 pi over 6. And when we multiply n by 2 pi by a half, we end up just getting n times pi. The 2 on the bottom and the 2 on the top cancel out. And it's going to be the same in the imaginary part. So 5 pi over 6 plus n times pi. So we're left with an n in our question, or an n in our answer. But have a look. Let's remind ourselves of the question. The question asked us for 2 possible values of w. That's the hint in the question for how many values of n that you sub in. Okay, so we always start with n equals 0. And for this question, we will just use 2 values of n. That doesn't mean that we go to 2. So this doesn't mean that we go to 2 for our n values. It means we use 2 values of n. So we're going to let n equals 0 because we always start with 0, and n equals 1. That's going to give us our 2 answers. So first of all, we let n equal 0. So the modulus remains the same. We're getting cos of 5 pi over 6 because this whole thing is going to disappear when we let n equal 0, plus I times the sine of 5 pi over 6. And down here, you're going to end up getting 2 times the cos of 5 pi over 6 plus 1 pi plus I times the sine of 5 pi over 6 plus 1 pi. Okay, and then your last job, because we were asked to give our answers in Cartesian form, is just to put these straight into the calculator. Again, make sure your calculator is in radians. For the real part, 2 times the cos of 5 pi over 6, that should give you minus root 3. For the imaginary part, it's going to be 2 times the sine of 5 pi over 6, so that should give you plus 1, and it's the imaginary part. You're doing exactly the same down here, so it's going to be 2 times the cos of 5 pi over 6 plus pi. If you want, you can have that bit worked out first. That should give you root 3. And for the imaginary part, it's going to be 2 times the sine of 5 pi over 6 plus pi, and that should give you minus 1i. Okay, and you'll notice that your two roots, or your two answers, they're very, very similar to each other. And just check that we've answered the question. Always go back and check that you've answered the question. We found our two possible answers, and we gave our answer in the form a plus bi. Okay, so hopefully that was of some help to you. We've gone through two questions there. So the first one, just to recap on it, was from 2017, and that was an example of where your power is a whole number. So it's z to the power of 4. We're just simply raising that complex number to the power of 4. 2019 was a little bit trickier. Again, like I said, most people get confused as to whether it's a fractional power or whether it's just a whole number power. Usually there's a hint in the question. In this question, the hint was we looked for two possible answers, and they also gave us an equation over here. Okay, so I'm just going to take you through. I'm not going to go through any more questions, but I'm going to take you through, just by looking at the questions, how do we know if they're a fractional power or not? So these are from various questions down the years. The first one, the complex number z has modulus 5 and 1/16, so that's our r, and argument 4 pi over 9, so that's our theta, and it's given in radians. Find in polar form the fourth roots of z. So the hint in that question, you're expecting 4 answers, so that's going to be my fractional power. I'm expecting 4 answers, that's the big hint, but it also gives me an equation here. So in other words, we're looking for w, so we would have to find the fourth root of each side. So we would end up with w is equal to z to the power of 1/4. There's my fractional power. This next question here, use the Myers theorem to show that z to the power of 10 is equal to that. So again, in the first part of that question, you will know what z is, and you're simply just raising it to the power of 10. So that's a whole number power. And this question, again, these are taken from 3 different questions, 3 different years, 3 different papers, but we're just looking at whether they're fractional powers or not. And the last one, use the Myers theorem to express this in its simplest form. There's no mention of 2 answers or 3 answers or 4 answers. There's no equation. It's simply taking a complex number and raising it to a whole number power to the power of 8. So that's a whole number question. Again, don't forget with the Myers theorem, you need to be able to prove it by induction. So I've given a link to that in the chat. And there's also another example there from 2018 of applying the Myers theorem with a whole number power. Okay, so hopefully that was of some use to you, and hopefully it gave you a better insight into the uses of the Myers theorem and how we work that out. Thanks for listening.